Okay, I think then let's start. I mean, first of all, welcome everybody to Regensburg. I mean, I already said hello yesterday for those who were there, but now this is the official welcome. So I'm glad that you're all here. I'm quite excited that we have such a big conference here. And let's hope that it will be an interesting conference with many good talks and inspiring discussions. And maybe before beginning, there are a few organizational things I want to, well, we have to do this first. And let me see. Okay, first of all, I wanted to present the organizational team. I mean, there is like Claudio Paganini. He's sitting over there. Then Marco van den Belzerano. So I mean, he takes care of the slides. So maybe you already had contact with him and emailed him the slides. Then there's Patrick Fischer and Christoph. Maybe he'll come a bit later, so he's not here right now. And then, of course, last not least, so this is our secretary who did most of the work of the conference, and also you should contact her concerning the reimbursement and all of that. And in case you have any organizational questions, just approach one of us and let us know what you need. Okay, then there are a few. Then next, I wanted to thank our sponsors. So first of all, of course, the University of Regensburg for giving us the opportunity to do this here. So they offer we can use the Mensa, all the facilities here, also lecture rooms and so on. Then we got funding by the Kepler Research Center for Mathematics. So this is like basically all part of our third-party funding goes into the center and can then be used for conferences and other events. Then there's the Heraeus Foundation. So this is one of our main sponsors. So this is they host events mainly in Bad Honnef. So there is a conference center there, but they also sponsor events outside. So we're very happy for financing us. They are also paid for this outreach event yesterday. Then there's the Filbert Foundation. So it's like a local organization here in Regensburg, which pays for visitors from abroad. So like many of you who come from outside Germany are paid by this foundation. And last not least, there's also the International Association of Mathematical Physics, which gave us some support. And I'm asked to make some advertisement for this organization. In particular, you become members, just some more information. So the membership, in particular for young people, it's not quite, you have a good deal, so to speak. I mean, so it's 30 euros per year, but the first year is free. And if you go to conferences, which are also partly sponsored by IAMP, then you get a reduced fee. Also, you get like whatever you see it here, discounts on books. You get a bulletin a few times a year. And now if you want to become members, then so you can go to their website, or you do this right now, you do this later, and then you can sign up and become members. Good. So now another organizational point is, how do we organize the discussions? This is, of course, an important point. And we set up this online platform, Slido, where you can go there right now. Also, we have this capture in the coffee room. Also, I have a few printouts here. So you can go there, and then you can suggest topics for the discussion. So questions, what would you like to discuss? And you can either put your name, or you can do this anonymously. And then you can also vote for those. So you can say, okay, thumbs up, and then we see which topics are of interest. And accordingly, we will set up the topics for the discussions, for the parallel discussions on short notice. And you always see the topics on our website in the program, and then you can go to the corresponding room. Okay, I think that's all I wanted to say concerning the organization. Are there any questions? Anything unclear? I mean, most of it, we put a lot of information on our websites. If there are other things, just let us know. Good. So now I want to come to the scientific part. I mean, today is kind of the geometry day. So we want to cover both classical geometry and quantum geometry and compare the two. And to set the stage, I mean, we also want to discuss all this in connection with causal fermion systems when we had this introductory school yesterday. And I just wanted to briefly explain how geometric structures come up in causal fermion systems. And I will be very brief and also postpone more to the discussions. And one gets the connection to geometry on various levels. Let's begin with the top level. Suppose we construct a causal fermion system in Minkowski space, or the one we saw yesterday, and then we introduce linearized gravity. So we perturb the metric tensor by linearly. And then one can ask the question, does the system still satisfy the Euler-Lagrange equations of the causal action principle? So is it still a minimizer of the causal action? And it turns out the answer is, it is a minimizer if and only if the linearized Einstein equations hold. I wrote them here. And here kappa, so the gravitational coupling constants, is related, or scales like epsilon square. This is like the regularization length. This is why you can think of the regularization length as the Planck length. And there is also a cosmological constant, which is undetermined in this approach. Okay, so this is just linearized gravity. Now one can go one step further. The whole setup is generally covariant, as we also discussed yesterday. And therefore, these higher order terms here can be translated into higher order curvature terms. So these are the corrections terms which we get there. Okay, so this is on the top level if you want to get the connection to the Einstein equation. But of course, here we put in that we have a causal fermion system constructed in a classical space-time, or even more in a perturbation of Minkowski space-time. Okay, now in the most bottom level, so on the most fundamental level, there's another approach which is quite old. I mean, I did this together with Andreas Grotz, a PhD student at the time. Suppose we start into the completely general setting with a causal fermion system, then space-time is defined as the support of the measure rho. Then one can introduce a notion of a spin connection, which is like a unitary mapping from one spin space to the other. So this is like a connection. It gives, generally speaking, and we saw yesterday, this kernel of the fermionic projector, P of xy, gives us relations between the space-time points. And out of those, one can construct like a unitary mapping, which is a spin connection. There's also a metric connection, and curvature is then defined via the holonomy. So this is a quite nice setup, and also one can verify that it gives the right correspondence to the Lorentzian curvature in a classical space-time. However, there's a drawback. Unfortunately, it is not possible, or it doesn't seem possible, to reformulate the causal action principle directly in this language. So Andreas tried this for quite some time to reformulate it in these geometric notions, but it wasn't successful. And therefore, there are other approaches. I mean, what one can do is also one can look for synthetic geometric notions. So the idea is, well, if we can't define the correct curvature quantities locally, maybe we can define them in bigger space-time regions. And to this end, we analyze like two-dimensional area change and matter flux together with Eric Curiel and Jose Isidro, who's here. And this connects to Ted Jacobson's derivation of the Einstein equations, kind of more thermodynamical derivation. So this is one thing we did. We also introduced the concept of total mass together with Andreas Platzer, a former PhD student. And more recently, we introduced quasi-local mass and synthetic curvature together with Nikki Kamran. So here the idea is like we just want to see the effects of gravity on large scales by seeing, well, what is this synthetic scalar curvature? Does it have a sign? What is the total mass? How is it related to the quasi-local mass? And so on. Good, and then there's one even more recent approach, which is work in progress together with Christoph. And again, we start in the completely abstract setting, but now we make use of the fact that the set curly F, in which this rho is a measure on curly F, as you probably remember from yesterday. And this curly F itself is a Banach manifold, and even more, it carries a Riemannian metric, namely just the Hilbert-Schmidt scalar product on the operators, on these Hilbert-Schmidt operators, gives the Riemannian metric. So you have like a very high-dimensional Riemannian metric, and space-time is a subset thereof, or is a submanifold thereof, depending on what regularity you assume. And then one can consider extrinsic notions of curvature, so like similar to the Gauss curvature, analyze the Gauss-Codazzi equations and all of that. And then the idea is that these Gauss equations should give a connection to the Einstein equations. And then there's one more thing one can do. One has this non-local kernel. So this Lagrangian is like a kernel which vanishes if x and y are not the same as long as they are sufficiently close together. So you have like a non-local kernel on small scales. And this can be used to smear out things in simple terms. So one can introduce then smeared derivatives. And the hope is that all of this will give, first of all, that this setting is really the one where you can reformulate the causal action principle in. And the hope is that this also gives a geometric derivation of generalized Einstein equations in non-smooth spacetimes. Okay, and hopefully we can discuss all this later. I think this is all what I wanted to say. And I think now we can move on to the first speaker.